And thank you for joining us. Today, we're excited to showcase a brand new tool within PlantPredict called Voltage Pro, designed for maximizing string lanes on utility scale PV power plants. Today's webinar will run approximately 50 minutes with a live Q&A session that may run a few minutes past the hour if you decide to stick around. Feel free to submit your questions anytime during the webinar, and we'll try to address as many as we can. A recording of the webinar will be shared in the next 48 hours, along with links to the special promos. So for today's agenda, we'll begin with some quick introductions, and then we'll jump into the product demo and a discussion of safety factors and delta T, followed by a business case describing huge cost savings potential when using Voltage Pro. Finally, stick around for a couple special offers, including a free trial of PlantPredict Pro and special pricing on Solar Anywhere datasets. With that, I'll hand it over to Terabase Energy's Director of Project Engineering, Jason Spokes.
Hi, everyone. Thanks for joining today. I'm really excited to be presenting on Voltage Pro. It's been a really exciting journey to see it grow from an idea to an Excel tool to now a cloud-based application coupled with PlantPredict. So I'm the Senior Director of Project Engineering at Terabase Energy. My background is electrical engineering. I have been in the electric power industry for over 20 years and in the large-scale solar industry for over 12 years. And with that, I will hand it over to Mark to introduce himself.
Thank you, Jason, and happy to be here as well. I'm happy to have this opportunity to speak about temperature and about Voltage Pro. I'm the lead researcher at Clean Power Research. Like Jason, I've also been around for a while in this industry, specifically in renewables. I've been around for about 20 years, EPC, development, academic research, corporate research, and I'm happy to talk about all things temperature today.
All right, thanks, Mark. And I'm David Spieldener. I lead the PlantPredict product team, and really excited about PlantPredict Pro and also what Voltage Pro brings to the table. This is a really great addition to the PlantPredict suite of tools. I've been in the industry for around 18 years, leading the PlantPredict product for the last 5. So just real excited to have so many wonderful participants, as this is a very well attended webinar. We're grateful for that. And just excited to show you what we got. So with that, I'm going to hand it over to our Vice President of Development Technologies and my boss, Tang Li, to give a little bit of an intro on Terabase Energy.
Thanks, David. Hi everyone. Thanks for joining us today as we continue our regular series of webinars, sharing news and updates about our products, as well as interesting topics related to the industry. As David said, my name is Tang Li. I'm VP of Development Technology. I'm responsible for our products and services that are geared towards the pre-construction phase of the project. I'll just take a couple of minutes today to introduce Terabase for those of you who are not familiar with us. Terabase is a venture-backed technology company founded in 2019 by a group of industry veterans from SunPower. Our mission is to accelerate the deployment of renewable energy, and we do that by offering digital products and automation products. Our team has deep industry experience. We've worked on large-scale projects, primarily solar power plants globally, and that experience is the foundation of our products and services. If you'd like to learn more about any of these products that are shown on the right here, please feel free to reach out to me or any of my colleagues. But without further ado, I'll hand it off to Mark to introduce CPR.
Sure, thank you, Tang. So I'm representing Clean Power Research here today. Our tagline, our mission statement is advancing the energy transformation. We're a global B2B SaaS company. And the main product, we have 3 main products, mainly focused on the utility segment, Power Clerk and Watt Plan. The one more that you might be more familiar with is Solar Anywhere. In Solar Anywhere, we serve over 250 plus solar industry accounts, mainly developers, banks, independent engineers, financiers. We're a bankable data set, both from the entire satellite historical record of roughly 20 years up to 7 days in the future for forecasts. And we also serve electric utilities and energy agencies, munis, IOUs, co-ops, and I'm happy to be representing Solar Anywhere here today. I'll pass it off to Jason, who I think is going to run the first of our several poll questions.
Yep. Hi, everyone. Okay. So the poll should be being distributed at this point. Looks like we've got results coming in. And it looks like, I'll give it a couple more seconds. And it looks like there seems to be some alignment that the development engineering phase of the project is really the focal point for when the string sizing should be sort of the best time for the string sizing to be finalized. So that's pretty interesting. Okay, so let's move on. So we're going to be going into a demo of Voltage Pro. But before we do, I'd like to talk briefly about the relationship between Voltage Pro and PlantPredict. Voltage Pro is tightly integrated with PlantPredict. When you create a project in Voltage Pro, a project of the same name is created in PlantPredict and is assigned as a string size type project. This helps facilitate searching and filtering of projects more easily within PlantPredict. Similarly, when you create and run a string sizing calculation in Voltage Pro, a parallel prediction is created in PlantPredict. And it's the prediction where the open circuit voltages are calculated for each time step of the simulation. Voltage Pro receives that information from PlantPredict and applies additional post-processing and safety factors, and is what allows us to generate the string sizing reports. If you want to see the underlying open circuit data for each time step, you can access this within the PlantPredict prediction. This is saved within the DC Fields nodal data and can be downloaded in Excel. It's also worth noting that the databases within PlantPredict, the module, inverter, and weather databases are also accessible within Voltage Pro. So these are not two separate databases. These are all referenced to the PlantPredict database. And so that, now that we have a basic understanding of Voltage Pro's relation to PlantPredict, we're going to take it for a live spin. I would like to highlight that we've just published a new in-depth user guide as of yesterday. This should not only help describe how to use Voltage Pro, but also explain some of the underlying models and equations that are used within the application. So at this point, let's hop over. I'm going to pull up PlantPredict. And this is where we're going to start to get into a Voltage Pro live demo. So at this point, I'm within my PlantPredict user account, and in the left-hand pane, I can access Voltage Pro here. So I'm going to click on that. And this pulls up the main Voltage Pro page. And what I see is a listing of all of the projects that I've created in Voltage Pro. And within each project, I can create one or more calculations. So for this live demo, let's create a new project. And I'm going to create a project in Ohio, and I'm going to call this Webinar Ohio Solar Project. And I know that my project latitude is 40.415. And I know that my longitude is negative 82.905. And when I enter that basic information, Voltage Pro recognizes the location and I can save the project. Now that I've saved the project, I'm going to want to add a string sizing calculation to it. So let's do that. Once I add the calculation, it immediately brings me to the calculation page, and my calculation is automatically named SCalc01. I can rename that if I want. I can also clone and delete calculations. And you'll see that there's some basic input information that I need to put on the left, and my results will, or additional information about those inputs, and ultimately the results will be on the right-hand side. So you'll see that I need to input weather data, module data, inverter data. I have some simulation settings that I can play with, and then ultimately I'll submit the calculation and obtain the results. The weather data. In this pane, we've got the meteorological data, and Voltage Pro is referencing the PlantPredict databases here. And I know that I want to use a multi-year weather data set. And my colleague David had previously uploaded a 20-year time series weather data from Clean Power Research, Solar Anywhere, for this project. So I'm going to use that. So it's pulling in the temperature data here. And at this point, it's pulled it in. There's some basic information about the data that I've uploaded. I'll click next. And this is a page that allows me to look a little bit closer at some of the temperature related data within that data set that I just loaded. So what you'll notice is over to the left, I'm displaying all of the years that were present in the data set that I just uploaded. I also am showing the minimum temperature for each of those years. And over to the right, this is representing the number of months, or the months that are present within that data set. So as you can see, for all of the years, my data set is full except for 2021, where I data. It looks like I only have January worth of data here. And you'll also notice that this negative 12 degrees is a bit lower than most of these other minimum temperatures, and that's probably because this is a partial year. So we're going to uncheck this, and when I uncheck it, notice that the average extreme annual minimum temperature of my entire data set is going to change. So it's actually going to get colder, negative 20 versus negative 20.3. And instead of having a 22-year data set, I now have a 21-year data set. I'm going to save this as it is because I want to have a more conservative cold weather temperature, and we'll talk more about how this extreme annual mean minimum temperature is used within some of the safety factors. So let's click next. Last but not least, I'm pulling in ground measurement data, in this case ASHRAE data from my nearest ASHRAE weather station to my project site. And we can see that this ASHRAE weather station is 26 kilometers from my project site. This is also used in some of the calculations and some of the derivations of safety factors. So let's click Save, and let's move on to our PV module. For this project, I know that I want to use a Longi solar module, and I think it's the very last one. It's the LR572HPH540M. That's the one that I'm going to use. I'll click Save. And then for my inverter, I'm actually going to filter by my inverters. I'll pick a SunGrow SG4400UD, and I'll click Save. And now it's immediately brought me to the Results tab. It skipped over the settings because I don't need to enter the settings. But before we run it, let's take a look at the settings just to see what I can manipulate. The first is the cell thermal model. I have an option of the heat balance model or the Sandia. Heat balance is the standard model or the default within PlantPredict and is also the standard model of PVsyst. I also can use the Sandia model if I choose. Cell temperature is critical to the open circuit voltage calculations. I have the conductive and convective coefficients for both. We talked about this at length in a prior webinar. I can also modify the maximum system voltage. By default, we pull in the maximum system voltage from the inverter file, but I can override this if, for example, I have components which have a lower maximum system voltage than the inverter. Last but not least, I can modify the ASHRAE extreme annual mean minimum temperature. This is primarily used in the linear calculation method. I'm going to leave it as default from the nearest ASHRAE station, and I'll click Save. And now I'm ready to run the analysis. You'll notice that for the linear method, or the most basic calculation method, which just uses data sheet and ASHRAE information, the calculation has already been completed, and that's 26 modules per string. To get the advanced method calculation, I'm going to need to run it, and that's going to go through PlantPredict. So let's go ahead and run it. Okay, so at this point, my calculation is running. And this is going to be going through PlantPredict. I've got 21 years of data, so it's going to take a minute or so. While we're waiting for the calculation to run, let's take a quick look at the user guide. I just want to point a few things out. So mainly I want to let everybody know that this is available. It helps explain some of the background information and equations and references used in PlantPredict, or sorry, in Voltage Pro. There's a couple of things that I want to draw attention to. We have a section on codes and standards compliance, and we list out the codes and standards compliance for the method 1, which is the simplified calculation that we're all familiar with, and the method 2, which is the PlantPredict simulation method. It is Terabase's position that when used with appropriate input data, these methods are compliant with these standards, codes and standards. And you'll notice that method 1 is compliant with more because it is a more conservative calculation. So just be aware that this table exists, and this table is also replicated on the output report. I also want to draw attention to one of our references, which is the Karen and Jane photovoltaic string sizing using site-specific modeling, which was published in the IEEE JPV. This really served as a foundation for which the basic approach that Voltage Pro is built on. So we've referenced this in the past, and I just want to let people know that it's there. There's a lot of information in the user guide, so if you don't catch everything that we're talking about today, feel free to take a look there. Okay, let's hop back over to our simulation, and it's getting close to being done. Keep in mind that this is pumping through, in this case, over 180,000 different open circuit voltages. So it is 21 years of 8760 data, and that's over 100 points that it's analyzing. Okay, so it's completed. And we can see under the advanced method, we're at 28 modules per string. We could generate a report, but let's hop through some of the results that are available to us in the web. So with the linear method, we're displaying the results from several different string sizes. And we can see that at 27 string, we were just over 1500 volts. So the result, or the correct string sizing in this case, was 26. Let's take a look at the advanced method information. And I'm not going to spend too much time here, but there's a lot here. We're going to talk in much more detail about some of the safety factors that are displayed here. But I want to let everybody know that this is a live results page. When I update any of these values, it updates my results. And what I have here is a number of safety factors that are applied on top of the simulation output. The simulation output with those safety factors applied is described down here in this table. And we've got basically 4 different ways of looking at open circuit voltage results. We've got the P100 VOC, which is the most extreme of the 21-year period, and then the P99.5, which is the 99.5 percentile VOC. We also are displaying this as MPP and open circuit cell temperature. So there's a slight difference between the two, and we think it's important to pull that out. The open circuit cell temperature is actually a little bit warmer and results in a little lower voltage. With the default safety factors, we're at 28 modules per string on this lower item, but we can manipulate these in real time and affect these values. By default, the cold weather variability is set to 0. We can calculate that based on our temperature data, and we are at a safety factor of 2.071. The table was updated in real time. The result of the P99.5 VOC at open circuit cell temperature is still 28 modules per string max, but by default, we typically keep this at a safety factor. Again, we're going to talk in much more detail about these safety factors later, especially the temperature-related safety factors. And the last thing I want to do before we move back to the presentation is show the report that can be downloaded. So we immediately download a PDF report and information about the input data that went into the simulation and the string sizing calculations. There's a summary of the method 1 calculation. We have the raw method 2 simulation output direct from PlantPredict. We have the safety factors that we just talked about, and we have the corrected simulation output with the safety factors applied. So this table is basically the same as what we saw in the display in the Voltage Pro. Okay, let's hop back to the presentation. Okay, so now let's focus on probably the most confusing part of Voltage Pro, and that is the air temperature data safety factor. That was one of the safety factors that we just saw in the demo. The objective of this safety factor is to correct for temperature bias in our satellite data. The safety factor itself is easy to compute using the equation highlighted here. It's simply the temperature coefficient of VOC, which we can get from the datasheet or pen file, times the air temperature delta T. The computation of delta T, however, is a little complex, so let's spend a few minutes on it. Delta T is the difference between the extreme annual mean minimum temperature from a long-term ground measured source of temperature data, in this case, Voltage Pro is using ASHRAE data, and the same extreme annual mean minimum temperature parameter from our satellite data set. So we're treating the long-term ground measured source as a source of truth. And in effect, we're calibrating our satellite temperature data with that ground source of truth. As described in the bottom left box, when our ground extreme annual mean minimum temperature is less than the satellite extreme annual mean minimum temperature that we're using in our simulation, this is going to result in a negative delta T, a positive safety factor, and increased safety margin. And this makes sense because when our source of truth is colder than the data we're using for our simulations, we want to increase safety margin. Conversely, on the box on the right, when ground extreme annual mean minimum temperature is greater than our satellite data extreme annual mean minimum temperature, this results in a positive delta T, a negative safety factor and provides justification to help reduce some of the safety margin. Okay, unfortunately, it gets a little bit more complicated with the air temperature data safety factor, and that's because Voltage Pro calculates the delta T that goes into that safety factor in two different ways depending on the satellite data source. So within Voltage Pro, there is a solar anywhere method of calculating delta T, and there's a non-solar anywhere method. Dr. Mark Perez is going to be speaking in a few slides and is going to go into much greater depth into the solar anywhere method of calculating delta T and the research that they've done on that. But for this slide, I really wanted to help visualize the difference in the two methods. On the left-hand side, we have a map of our Ohio project site location, and it's identified by the green arrow. And we have a clustering of nearby ASHRAE weather stations around it. For the non-solar anywhere data, which is the middle box, we're comparing the extreme annual mean minimum temperature of the project location satellite data set with the extreme annual mean minimum temperature of the closest ASHRAE weather station, which in our case is 26 kilometers away and is identified by this A arrow pointer. For this example, I've downloaded 21 years of NSRDB data, and I can see that the ASHRAE extreme annual mean minimum temperature is several degrees colder than my NSRDB satellite data set. It's 3.58 degrees colder. When multiplied by my module temperature coefficient of VOC, I get an air temperature data safety factor of 0.97%. So this 0.97% would be applied on top of the simulation open circuit voltages. Now let's look at what's happening when I use solar anywhere data. In this case, my project data set isn't used at all, and that's because my project data set is at a different location than my ground reference points. Solar Anywhere has done the legwork and has already compared every ASHRAE ground measurement station with their own Solar Anywhere satellite data, so that they're comparing two co-located sets of data. They then interpolate between those points to derive a delta T for the specific project latitude and longitude of my project. And again, Dr. Perez is going to speak in much greater detail on how the delta T was derived and the work that they've done. But the advantage that I want to really point out here is that with the Solar Anywhere approach, it's more of an apples to apples comparison because we're comparing temperature data from two sources at the same location. And in this particular case, my delta T is negative 0.697, and my safety factor is only 0.188%. So because we're comparing apples to apples, we're actually, in this case, have a much lower safety factor. All right, and then the last slide that I'm going to speak to is to talk about the cold weather variability safety factor. This one's a little bit easier to wrap our heads around. As I mentioned before, this is treated as an optional safety factor in Voltage Pro and only applied to the P99.5 results. By default, it's set to 0%, but it can be automatically computed and included in the safety margin on demand. The objective of this safety factor is to apply higher levels of safety margin where extreme cold weather temperatures have higher variability from year to year. The basic equation for the safety factor is highlighted in yellow and should look familiar. But in this case, the delta T is derived completely from the project data set. In this case, the delta T is defined as the difference between the extreme minimum temperature of the project data set and the extreme annual mean minimum temperature. So to kind of restate that in layman's terms, we're comparing the most extreme low temperature from our satellite data set with the average annual extreme low temperature from the same data set. Voltage Pro calculates this safety factor the same no matter the source of the weather data. And just for comparison's sake, I've included this safety factor calculation for this Ohio project site from 2 different satellite data sets over the same 21-year period. So on the left, I have NSRDB, and on the right, I have Solar Anywhere. They're both calculated the same way, just using their respective data sets. And the NSRDB data resulted in a 1.72% safety factor, whereas the Solar Anywhere resulted in a 2.07%. Okay. So now it's time for our poll number 2, which should be live at this point. And the question is, what weather data do you use for simulating open circuit voltages for string sizing? And the results are coming in, and there seems to be a strong majority using hourly time series, although there's also a pretty large percentage of folks using TMY data. We'll let that go for another minute or so. All right. So yeah, again, 54% are using hourly time series data, 26% using TMY data, 11% unsure, 8% using field measured data, and 2% using sub-hourly data. So that's pretty interesting. All right, I'm going to hand it over at this point to Mark, who's going to take it from here, talking about some of the research that CPR has done into the air temperature data safety factor. Mark?
Fantastic, thank you. So first, I'd like to touch upon this point that's relevant to the last poll question regarding choosing, which choice of data do you use? Do you use TMY or do you use time series data? So I'm going to underline the importance of using time series data for this purpose. Typical meteorological year data is just that, it's typical. It's an averaging sort of exercise where you select the average January from the historical record and the average February, and you piece that together into a kind of pseudo year that approximates the average, but still has the variability characteristics that you would see in any given individual month. So it's a useful exercise, but it's essentially you're trying to find the central tendency. And with the extreme value statistics that we're looking for here, the extreme annual mean minimum temperature, that's at the tail end of the distribution. So you're not going to capture that in this typical meteorological year. And just to evidence this point, I pulled for a single, or for all the locations, all the ASHRAE locations that were previously mentioned. There's roughly 9,000 throughout the world. I plotted at right here, this is an XY plot showing the minimum mean temperature, or the minimum temperature from TMY compared to the mean minimum temperature from the time series. And any of the points that do not line up directly across that very thin diagonal red line, these are outliers. So this means there's a difference between what the time series is saying and what the TMY is saying from the minimum temperature standpoint. So the point is you'll get somewhat of an erroneous answer. So TMY is good for doing P50, but if you're doing extreme value statistics and the extreme annual mean minimum temperature is one of those statistics, you're going to be a little bit off base. So next slide, please. So how accurate is the satellite data relative to ground? So satellites use radiometers in order to measure the radiance of the ground, because in the radio frequency, anything emitting thermal radiation is also emitting radio frequency, and you can use these sensors called radiometers, which are installed on these satellites, in order to infer the temperature from the ground with more or less with decently good accuracy. And the advantage of the satellite record is that it's available everywhere from the geostationaries. We have 20 years of data stretching back to 1998, so a little over 20 years of data. So it's really advantageous in that it's available on a gridded basis at the 10-kilometer spatial resolution everywhere on every continent across the entire world for 20 years. So ASHRAE is discretely, you have to interpolate ASHRAE station data or use the nearest neighbor as shown previously at discrete locations, and they're not available everywhere, as I'll show on one of the next slides. And so we calculated this delta T. So what's the difference between the satellite record in terms of extreme annual mean minimum and the ASHRAE record at the specific ASHRAE sites? So next slide, please. So these are the ASHRAE sites aforementioned. There's almost 9,000 of them scattered around the world and heavily concentrated in the eastern part of the continental United States and in Western Europe. Makes sense. These were probably the most technologically advanced areas, and the ASHRAE stations started being installed in the first part of the 20th century. I think there are even some that stretch back further than that. There are plenty in Japan and in Eastern Australia as well. Okay, so next slide. So to show what the satellite record looks like, this is gridded data at the 10-kilometer basis of the absolute minimum dry bulb temperature for every single point on the planet for a single year, 1998. If you'll go to the next slide, this is another individual year, 2021, and you'll notice that they're not identical. And this is another way to underline the importance of not using TMY, because with TMY, you'll select January from 1998 and February from 2021, for instance. So you might not capture the actual mean minimum temperature across the entire historical record. Perhaps you do, but in many cases you won't. Okay, next slide, please. To show the power of this data, I also plotted the distribution. These are density plots of the minimum temperature for every point on the planet. So in degrees Celsius on the x-axis, so density plot similar to a histogram for every individual year from 1998 through 2022. And the vertical dotted lines here that I've pictured are the medians of each of these distribution. Dark blue is 1998 and white is 2022, so it gets lighter as we go further closer to present day. And you'll notice heuristically, if you look at these vertical lines and their colors, that as we move to the right, they're getting lighter. So as we approach present day, the minimum temperature on the planet, the median of the minimum temperature across the planet is getting warmer. And this is a testament to the effect of climate change and underlining the importance of repeating this sort of analysis with some degree of regularity. Okay, next slide, please. Another way to visualize this, the fact that these numbers are changing over time, this is the true global minimum temperature across the entire planet. So this is the absolute minimum for any point on the planet, year by year from 1998 through present day. And I put a linear trend through this just so you can see that it's going up heuristically. And I've highlighted with this orange line the mean across the entire historical record. And as you might expect, if we progress, as we move forward into the future, there probably will be more points above the mean line. So therefore, the orange line inexorably will continue to move upwards over time. Again, underlining the importance of repeating this analysis. Okay, next slide, please. So here's the meat of the analysis. This is the delta T satellite to ground. So this is ASHRAE minus satellite. So if ASHRAE is less than satellite, then it will be blue. If ASHRAE is greater than satellite, then it will be red. As you'll notice, most of the points are blue. And the reason for this is the ASHRAE record in many cases is longer than the satellite record, so it has more time to capture the colder temperatures. As I mentioned previously, things are getting warmer on this planet as we evidence, so likely that mean will increase. but that's the reason why it's largely blue. The other point I want to highlight with this analysis is that there are regions that are red where the inverse is true. So it's important to, there's a spatial difference in terms of this delta T. It's not monotonic, so it's super location dependent. And interestingly enough, the areas in which ASHRAE is warmer than the satellite indicates are areas in the mountainous regions. So the Himalayas, the Hindu Kush, the Alps, the Caucasus, the Rocky Mountains, etc. So that's just an interesting artifact, probably linked to the calibration of the radiometers on the satellite, if I had to wager a guess, but also underlining the importance of this regional interpolation. And the way we got this, because we ran this analysis, this delta T analysis at the discrete ASHRAE sites, the roughly 9,000 I pictured earlier, and then we spatially interpolated them using bilinear interpolation. So that way you can get a delta T anywhere on the planet quite easily. Okay, next slide, please. So I've demonstrated, hopefully, that we can generate site-specific delta T with Solar Anywhere sites. So again, Solar Anywhere is a full historical time series data set with 20+ years of record at the 10-kilometer resolution, 10-kilometer hourly resolution, and we can even go higher in certain places in North America, for instance. We can go down to 5 minutes in 1 kilometer. And this Solar Anywhere data, which is constantly being updated, can keep your analysis up to date. And we will give you 1 year of access to the latest data for each site with our promotion that I'll describe later today. So thank you very much. And I think at this point I will give the microphone back over to Jason.
Yeah, thanks, Mark. Appreciate it. Great, great information there. So at this point, we have our poll number 3, and that should be live right now or being distributed. Looks like responses are coming in. What is the primary barrier to using simulation-based modeling for string sizing? And we'll give it a few minutes. Seeing some statistics coming in. It looks like kind of similar numbers coming in for lack of industry consensus at about, and risk of IE, OE, AHJ rejection. Okay, so it looks like the polls have closed. Looks like a majority, 38%, believe that lack of industry consensus is one of the biggest barriers. 28% with risk of IE, 16% lack of software tools, 14% lack of technical knowledge, and 5% inverter warranty risk. So one of the things that we're hoping to do with Voltage Pro is really start to build some industry consensus. So it's good to see that we're attacking that particular problem. All right, at this point, I am gonna hand it over to David, who's going to talk a little bit about a business case study for this project in Ohio using a longer string length. David?
Thank you, Jason. So now that we've seen how to use Voltage Pro to understand the limits of how many modules we can safely and effectively string together in series, the big question is, what difference does an extra module or two make? We're using the dev platform that's also included in the PlantPredict Pro subscription. I ran a couple of simulations on a potential project site in central Ohio. For this project, I'm targeting a 100 megawatt solar power plant. I want to model this plant using both 26 module strings and 28 module strings. The tracker that I plan to use will be a 3-string tracker, so the tracker length will be 78 modules and 84 modules respectively. As you can see by the table on the slide, we were able to reduce the number of strings by 7.2% using the 28 module string, which then flowed through to a similar reduction in the number of combiners and harnesses. The DC installation labor savings are worth 1/10 to 3/10 of a cent on a cost per watt basis. Furthermore, my DC cable length was reduced by over 100,000 meters. So if you figure $2 to $3 a meter, that could save us $200,000 to $300,000 in cabling material alone. For this analysis, we are figuring that the inverter rating stays the same. However, this is another area that could result in some additional benefit. You may be able to uprate your inverter and go with a tighter voltage window. We recommend that you check with your inverter manufacturer after running a Voltage Pro analysis to see what they think. As mentioned earlier, you get 7.6% more modules per tracker row, which results in a reduction of trackers by around 7%. This means 7% fewer tracker motors, 7% fewer controllers, and 7% fewer drive foundations. All of these reductions saving us money. Overall, I think it's safe to say that you could save around 6 to 8 tenths of a cent on your EPC costs when you factor in all the electrical, mechanical, and labor cost savings. And the best part is, as long as you are able to maintain the same GCR on your site, you won't notice any meaningful impact to your energy yield, which means these cost savings will flow right to your LCOE and will have a net positive impact on your IRR. In summary, you can save between $600,000 to $800,000 on a 100 megawatt power plant by increasing your module strings by 2 modules. So let's move on to our next slide. As we look at our PlantPredict pricing table, I want to point out that Voltage Pro is only available within our PlantPredict Pro and Enterprise pricing tiers. In the case of the Pro package, in addition to Voltage Pro, you get 3 user licenses, full access to all core PlantPredict features, plus the dev platform. All of this for the very reasonable annual subscription price of $6,000. We also offer additional users for $2,000 per user per year. So think about it. You can save $600,000 on a single project with a $6,000 subscription. What a deal. Now, if you're a larger organization, you can take advantage of our Enterprise package, which gets you all the same benefits as the Pro, but you get 10 users instead of 3, and you also get access to the PlantPredict API and SDK, which stands for Software Development Kit, which are a very powerful tool. Can create a tremendous amount of value. You also get enrolled into our concierge support plan. All right, move on to the next slide. As part of this webinar, we are offering you a free 30-day trial of PlantPredict Pro simply by using a special promotion code VOLTAGE, VOLTAGE. You simply need to sign up for a free PlantPredict account at www.plantpredict.com and then go to the subscription page. Click on the promo code button in the upper right-hand corner of the screen, enter your promo code, and then celebrate with some confetti. I will now hand it over to Mark to discuss another special offer that is part of this webinar.
Sure, thank you. So I'd like to introduce a rare thing for Solar Anywhere. I think this may be one of the first times we've offered such a promo, but currently in the context of this collaboration with Terabase, we're offering limited time, up to 60% off promo code for Solar Anywhere sites licenses. So we're offering the sites licenses at our minimum price, which is I think the minimum volumetric price that we offer at around $1,200 per site. And this expires on March 31st, 2023. If you want to learn more about it, you can contact Clean Power Research at the link below and use the promo code when you check out. And don't forget to read the fine print. You can also celebrate with confetti as you do with your Terabase deal.
All right, and now we're going to go to some live Q&A. And first question I'd like to address is, yes, this webinar recording will be available. So if you're registered, we'll be sending out a link in the next 48 hours with this webinar recording, along with the information about those couple of special promos. So now jumping into questions, I'm kind of grouping them together here. So several questions about, have any independent engineers accepted this approach? And is this methodology accepted by the AHJ for large-scale solar projects? Is there consensus amongst independent engineers on whether to use P100 versus P99.5?
Yeah, I'll take that one, Rafal. So these are good questions, and you know, to answer simply is we know that independent engineers and owners engineers and AHJs are accepting simulation-based results for string sizing, but as you know, some of the polls have kind of borne out that the lack of industry consensus is, what we see is that people are doing this slightly differently, with different data, different safety factors, different sort of approaches to the modeling using different tools. And as a result, it sort of spans a wide range of results. We're really hoping that Voltage Pro starts to build some industry consensus on how we should talk about string sizing and some of the standard inputs and standard safety factors around that. I don't have any evidence that independent engineers or AHJs have accepted this, but this is a brand new product that we're just releasing. And so we would love some feedback from our colleagues who are using this on that. So, yep.
All right, couple questions here about string lengths. How much longer do string lengths typically get? And do string lengths ever increase costs? Longer sizes ever increase costs?
Yep, I can take that one as well. So with Voltage Pro, I would say typically 1 to 3 modules per string is what we're seeing for crystalline silicon modules. Does it ever increase cost? There probably are some edge cases where it could. When things don't physically fit as well on a racking solution, or you need to add additional piles, things may not scale linearly from a cost standpoint. It's possible that a longer string length may not fit as well within a MPPT voltage window. So there could be some reductions from an energy standpoint, but generally speaking, what we've seen is that typically this is a pretty safe cost savings. But yeah, there probably are some edge cases where it could increase cost.
All right. Let's see. How is the string size determined in the standard PlantPredict package?
It's just using the linear method. So it's a very simple calculation using datasheet or pan file coefficient of voltage and the ASHRAE extreme annual mean minimum temperature.
Okay, and here I have a couple questions about Solar Anywhere. So I'm starting with, can Solar Anywhere data be reused for predictions? And do we need Solar Anywhere sites or Solar Anywhere tiles are sufficient?
Is this question for me?
Yes.
It could be used for multiple purposes. The sites data will give you access to the entire historical record for any given site, so that would be sufficient for simulation. You could pull it into PVSys or any other simulation software that you might use to simulate PV production. So if you have a sites license, you will have access to that from a simulation perspective. I don't know if that answers the question appropriately.
And then how much does Solar Anywhere data cost?
As mentioned on the previous slide, it's a sliding scale based on volume. There's a volumetric pricing component, so the more sites you get, the lower the price becomes. And the promotion that we're currently offering through the end of March brings the price for sites down to that minimum price, that minimum volumetric price, which is I think 1,200 per site or whatever it said on the previous slide.
Okay. Can you please explain how to integrate SAM and bifaciality?
Sure. So we do have simulation code on our end. Really, we expose PVlib now, so you can model a bifacial PV using PVlib if you want. You can also, if you have a sites license, download the data and plug it into any number of simulation software protocols. Could be SAM, could be PVSys, for instance. We do have a specific format. There's a specific format for PVSys, and when you In the drop-down menu on the user interface, you can select PVSYST format, and then you can get the data all ready to go into PVSYST simulation software. So that's how you would use the data in those simulation code bases. But you can use, it's a time series file, so as long as you have a simulation code base that can, or software that can read time series data for solar and understand the timestamps and everything, then you could use it with whichever one you're most familiar with.
Jason, do you have anything to add about SAM and bifaciality? How to integrate those?
So I'm not an expert in SAM, but my understanding with SAM is that the bifacial voltage gain, or the cell or the module voltage gain associated with bifacial gain is incorporated into the SAM open circuit voltage output. If that's the point of the question, then my understanding that that's correct. It's the same with PlantPredict. So when you run a simulation in PlantPredict, the effect on voltage from bifacial gain is incorporated into the model.
All right, so we're at time, but we're gonna keep on going with the questions for a couple more minutes, so please stick around if you can. Several questions about inverters. What happens when the voltage of a string exceeds the inverter limit? That's one question. And then have you evaluated the tool with inverter manufacturers?
I don't want to speak for any specific inverter, but I would say generally speaking, inverter manufacturers will include some safety margin in voltage for maximum system voltage. So I think it's safe to say that typically there will be some safety margin. So if you go to 1501 volts, 1502 volts, that's probably not going to be a problem. Of course, that needs to be verified with the specific inverter manufacturer. I think it's important to remember that in these, when we're looking statistically at P100 and P99.5 open circuit voltages, this is assuming that the plant is sitting at an open circuit condition for its entire life. In reality, most of the time, it is in an operating condition, operating closer to maximum power point, so it is not seeing anywhere close to those open circuit voltages. So there's a level of conservatism already built into this modeling, if you will, and the results, if you will. So I'll leave it at that. Happy to take that one offline and talk more about inverter specific, inverter manufacturer specific information.
All right, another question here. What happens if you have access to other ground stations data? How can those measurements be integrated in the analysis?
Good question. So we can, so you can override the ASHRAE extreme annual mean minimum temperature as I showed in the demo, but the derivation of the delta T today for solar anywhere data is done through the research that Solar Anywhere has done comparing themselves to ASHRAE data. And one of the challenges of using other ground reference data, is that ground reference data exactly co-located with the project site? Because if it's not, if they're some distance apart, then you're not really comparing apples to apples. That's really the value that Solar Anywhere has brought into this sort of analysis, and we want to expand that to also include other data providers and other ground temperature sources. But for today, the CPR specific research is only used in conjunction with that ASHRAE data.
Right, and I'd like to add on to that point. It's not only the spatial location piece, it's also the temporal range. ASHRAE has the advantage of, these are stations that have been installed decades ago. They have a very long historical record, so they're able to capture those extreme value statistics, like the extreme annual mean minimum temperature, pretty effectively. If you have a shorter time span, it may be that you don't get close to the extreme annual mean minimum temperature. It's sort of the same differences you'd get when you use TMY versus a long time series sort of data. So if you're talking about a meteorological station you install pre-construction to assess the local meteorological conditions, you may not get close to the extreme annual mean minimum temperature, and then you would be off if you were to use that sort of data.
All right, question for you, Jason. Is Voltage Pro based on VOC or MPP calculations?
Well, all of the results that we present are VOC, so they're the open circuit voltage. But we calculate that open circuit voltage both at the MPP cell temperature and the open circuit cell temperature. And let me kind of provide some more information on this. In the PlantPredict module model, for each time step, PlantPredict is determining that IV curve for that time step. And so PlantPredict has both the MPP voltage and the open circuit voltage at that time step. So we're taking the open circuit voltage at that time step, and we're calculating it at both the MPP cell temperature and the open circuit cell temperature. Why is that important? If I have a string that's operating at MPP and then it instantly is open circuited, it will take some time for the cells to warm up a little bit to that open circuit cell temperature. And so we want to provide that MPP open circuit voltage, if that makes sense, the open MPP temperature open circuit voltage. I know that's kind of a brain teaser, as well as the open circuit cell temperature open circuit voltage. Because that's more of a steady state condition if the string is open circuited and left open circuited for some period of time. So we're presenting both in Voltage Pro. Yeah, hopefully that answers the question.
All right, we'll take a couple more questions. Jason, have results been compared with PV Tools string length calculator put out by DOE and Lawrence Berkeley National Lab?
So we have heavily leveraged the approach taken by the Lawrence Berkeley Lab string calculator. That particular model is using is based on pulling in NSRDB data and running the open circuit voltage calculations using the Sandia open circuit voltage equation. So we're using the primary difference is that we're using PlantPredict for that module model as opposed to the Sandia equations. And we presented in a previous webinar why we think that that's not only a valid approach, but it actually brings in some additional accuracy that isn't present within the Sandia model. One of the main being that you can use a module manufacturer's pan file, which you cannot use in the Sandia model. So we've sort of looked at that, and we came to the sort of consensus that we're better off using PlantPredict. But yeah, the general approach and the general the foundation of what we did with Voltage Pro is actually based on that Lawrence Berkeley Lab approach, and this is what I pointed out in the user guide is we referenced that particular IEEE paper that was put out by that team.
And as Jason mentioned, we did cover a lot of the research that went into Voltage Pro in an earlier webinar. That is on the TerraBase YouTube channel, and we'll include it in the follow-up email to this webinar. So Jason, this might be the final question here. Some clarification about your previous answer. Can you please clarify whether the final string length is determined based on open circuit or MPP conditions?
Yeah, good question. So the final string length in the Voltage Pro app results page is based on the open circuit cell temperature. The report that we generate, we're careful not to say that this is the answer or that is the answer. We're providing you with the information that an engineer can make that decision. We're providing you with all of the information, but not necessarily saying that the magic answer is 28 or 27. In our internal practice at TerraBase, we're using the P99.5 open circuit voltage at open circuit cell temperature. But we're a little bit careful not to take a extremely strong position on that. We provide you with all of the results in the report for both of the cell temperatures, if that makes sense.
All right, so we're going to end it there. Thanks for joining us today. Once again, we'll be sending out a link to the webinar recording in the next 48 hours. There's also going to be a follow-up survey after this webinar. So if you have any additional questions, if there's any additional topics you would like us to cover in a future webinar, please let us know in the comments field. Once again, thanks for joining us and have a good day.